In today's class, we'll look at S and ABCD parameters with respect to two ports, and we'll also look at resonant circuits. So you may recall from your earlier courses that for any two-port network, you can define different sets of relations between the currents and the voltages, between the input port, which is usually 1, and the output port, which is 2. For example, the Z parameter relation is the voltage matrix is the Z matrix times the current matrix, or it's often represented as V equals Z times I, where all of these are matrices. Similarly, you can define your Y parameters, H parameters, and your G parameters. Now, what we notice is all of these relate your voltages and currents of the two port. However, if you have this is valid for any two port. However, excuse me, for a distributed network, you talk of incident and reflected waves. Okay, so the two quantities we want to relate are the incident and reflected waves. So this naturally gives rise to what are called scattering parameters. So the relationship is the reflected waves, in this case voltages, represented by a matrix VR, equals the product of the S matrix and the incident voltages. So let's look at the two port again. Now, one important difference is the scattering parameters are defined with respect to a characteristic impedance of the system, which is Z0. So you have the input incident, which is Vi1, the input reflected voltage, which is VR1, the output incident, which is Vi2, and output reflected, which is VR2. So of course you have VR1, VR2 is the S parameters times the Vi1 and Vi2. Now what is also commonly done is the reflected and incident waves are normalized with respect to the characteristic impedance. So you define 4 other quantities. So you have Aj is Vij over root of Z0. That is, A1 is Vi1 over root of Z0 and A2 is Vi2 over root of Z0, and these are the incident quantities. The reflected quantities are again Vrj over root of Z0. The main idea is Aj squared and Bj squared stand for the powers of the incident and reflected waves, and Sij, which are the scattering matrix components, they are often, you will see, often represented in decibels or dB. I am sure you must have learned this in a previous course. Decibel is nothing but 20 log of the value for a linear value. And now you can define S11 is B1 over A1 when A2 equals 0, and this is VR1 over VI1, and this is often called gamma, which is the input reflection coefficient. S21 is B2 over A1 when A2 is 0, which is VR2 over VI1. So what does this mean? There is an incident wave at the input, and the reflected wave at the output when an wave Vi1 is incident at the input is called S21, and this obviously stands for the gain of the 2-port. And note that S21 squared is VR2 squared over Vi1 squared, and you can rewrite it slightly differently. And this is called the power gain. If you express them in dB, they'll have the same dB value, because for power quantities the dB is taken as 10 log instead of 20 log. The other important quantity S22 is B2 over A2, which is VR2 over Vi2, and this is the output reflection coefficient. Finally, S12 is B1 over A2 when A1 equals 0, which is you have a wave Vi2 incident at the second port and you have a reflection at the input port, and this is your reverse gain of your system. So normally what do you want? Normally if your system is very well matched, if your 2-port is well matched to your characteristic impedance Z0, there won't be any reflections, and therefore S11 would be very small. Similarly, if the output is very well matched, S22 would be very small. And if your system has a lot of gain, you want S21 to be large. You want to get as much gain as possible from your system. And of course S12, which is your reverse gain, usually if you look at amplifiers or normal systems, you want them to have a gain in the forward sense, but you want the reverse gain to be as low as possible, because as we'll see later, that also leads to instabilities. Now, a short note on units that we'll see in this course. So let's say X is a linear electrical value. Okay, for example, it could be voltages, currents, and so on. So X in dB is nothing but 20 times log to base 10 of X. Now if you have a quantity which is in power, P, which is proportional to V squared or I squared, for example, P in dB is usually 10 log the power. Now one other very important quantity which you will see is dBm, and that is, so if you look at the decibels, dBs, it's usually a relative quantity, whereas dBm is an absolute quantity. It's 10 log of P over, it's the power relative to 1 milliwatt, and you take 10 log times that. What that means is 1 milliwatt corresponds to 0 dBm, obviously, because 10 log of 1 is 0. And if you have 10 milliwatts, this corresponds to 10 log of 10, which is 10 dBm, and so on. And one other useful thing to know is, if your characteristic impedance is 50 ohms, 0 dBm corresponds to approximately 223 millivolts RMS. That is, the voltage swing of a 0 dBm signal at an impedance 50 ohms is 223 millivolts. And you will also occasionally see people talking about dBV, for example. So if you have a 1 volt signal, that could correspond to 0 dBV. Okay, so that is occasionally used. The other very important quantity which is used is called dBc, which is power with respect to the carrier. Okay, so you'll see this used quite often. Okay, so what that means is, the C means the 0 dB reference is power of the carrier. Okay, a carrier is usually the reference signal. Okay, I'll give you a simple example. So this is the reference signal, and you'll see that this is often used for noise or distortion, sometimes interfering signals, and so on. So to give you an example, you could talk about, so let's say your desired signal is here, so let me call this omega RF, and you have some kind of interfering signal. So you could say that, so let's say this was 10 dB. You could say interferer is, you could say interferer level minus 10 dBc, or so let's say this is the amplitude in dB, and of course this is omega. Similarly, so let's say this is noise per spectral density. We'll look at this in more detail in a later class, but So let's say if you have your desired signal and you have a noise floor, okay, some random broadband noise. We'll look at what noise is, but I think most of you know enough to understand this concept. So which is, you have some kind of broadband noise in the system. So you could say, for example, that the noise is at minus 80 dBc with respect to the signal, or the noise floor is, you could say, you might hear somebody saying the noise floor is minus 80 dBc. Okay. So now we'll move on to ABCD parameters. So this is very useful for cascaded two ports. And so if you have it, let's look at the two port again. So the only thing to remember is, so you define I1 as the current going in and V1 at the voltage at the input port, and the V2 is the voltage at the output port. The important thing to note is that I2 is now defined as the current leaving the port. So it's the opposite direction as what we assumed, as what we normally assume for two port, let's say Z, Y, H and G parameters. Okay, and you could say the relationship between the input and output parameters are V1 I1 is ABCD times V2 and I2. Okay, so let's say you have a cascade of two port networks. Then you can say that, so this is the relation for the first two port, and the second two port can relate. So let me call this ABCD1 times V3 I3. So what that means is, there's a very straightforward relation between the V3 I3 and V1 I1. So as you can see, this is very useful for cascaded systems. Okay, so now that we are done with looking at two ports, so at least a quick introduction to two ports that we'll need to understand what we are going to be studying over the next couple of classes. Let's look at the concept of resonance. So what you'll see is, all narrowband systems employ resonance. Okay, so most RF circuits, for example, we have tuned amplifiers which are band pass. You need impedance transformations, that we'll be seeing that very soon over the next few classes. And a little bit later in the course, we'll be looking at RF oscillators. So they employ resonance. So you might remember from your earlier courses that you have two kinds of resonance. You have series and parallel resonances. So what we'll do is, we'll take the parallel resonance, look at it in a little bit of detail. Then we won't have time to cover series resonance in a lot of detail, but what I want you to do is go back to when you go back as a homework, I want you to go back and try to derive the same expressions for the series resonance circuits. Okay, so we're going to look at parallel resonances. in this class. So let's say we have a current which is driving a parallel RLC network. Okay, and let's say the current has a certain profile, so it has an I peak. Okay, and this is your IN. Okay, so what do you know? You know intuitively at low frequencies, you know that it should behave inductively. Okay, so you know that at low frequencies the inductance, at DC it's of course a short circuit, at low frequencies the inductance impedance would dominate over the C and R, and capacitance of course would be a very large impedance. Okay, so you know it's inductive, and you know at very high frequencies it's capacitive. Okay, so what does this mean? If you had to look at the impedance of the network as a function of frequency, let's say the magnitude of the impedance, you know it looks inductive, which means it's linear with frequency at low frequencies, and you know at very high frequencies it's going to have a 1 over omega c kind of expression. So what is it going to look like here in between? So let's say you try to calculate the admittance y of omega. You know that's 1 over r plus j omega c plus 1 over j omega l. Okay, which is 1 over r plus j times omega c minus 1 over omega l. So at resonance, the impedance is completely real, and so let's call the resonant frequency omega naught. So you have omega naught c. At some frequency omega naught, you would find that omega naught c is 1 over omega naught L, and this frequency is the resonant frequency. And so you can derive the very well known expression for the resonant frequency of a parallel LC network. Okay, so this is a very common result and which you need to know. Now another note, I want you to note that the omega naught is the angular frequency and f naught is the frequency in hertz. Okay, so I don't want you to confuse these two. Okay, so this confusion is very common. Okay, so this is radians per second and this is in hertz. Now we also know that y of omega naught now is 1 by r, which is purely resistive. Okay, so what that means is at resonance, so your equivalent circuit is simply this. So now we are in a position to plot the impedance in a little bit more detail. Okay, so if it was inductive it would go this way, and this is your omega naught. Okay, and let's also plot the phase. Okay, so what happens at very low frequencies when it's inductive? It's going to have plus 90 degrees, and you know at very high frequencies when it's capacitive it's going to have minus 90 degrees. So you have some kind of, and of course at resonance it's purely, impedance is purely real, so it passes through the 0 degree point. Okay, now some very convenient on-chip values. What you'll see is, so something to remember, right? 1 nanohenry in parallel with 1 picofarad resonates at approximately 5 gigahertz. Okay, not exactly, but approximately 5 gigahertz. And what you'll find is, for resonant circuits, a few hundreds of femtofarads to a few picofarads is quite common. Similarly, for inductors, you could have anywhere from a few hundred picohenry to several nanohenries. Those are very common values. Now we'll also define what is called the quality factor of resonance of the resonant circuit. Now the first physical definition is Q is omega times the energy stored by the average power dissipated. Okay. Now what do we know? We know that at omega naught, V out is I in times R. What does that mean? So you have the inductor and the capacitor. Now their impedance cancels out, but there is actually stored energy going back and forth between the L and the C. Okay, there is stored energy, okay, going back and forth between L and C. Okay, so what is the total energy stored? So we know that it's half CV squared is the peak energy stored in the capacitor, and we know V peak is I peak times R. Okay, what is the average power lost, power dissipated? It's I RMS squared times R, which is I peak squared times R over 2, because I peak over root 2 is the RMS. So what does this mean? Q is omega naught times half C I peak squared times R square. Sorry, it looks like there's a problem. Okay, that's better. I peak squared times R squared over half I peak squared times R, and we know omega naught is 1 over root LC. So this means it's CR over root LC equals R over root of L over C. Okay, and an intuitive check is, you know that if let's say your resistance is infinite, that means that there is no power dissipated in the system. Okay, and what that means is your Q should be infinite, and that makes sense here, right? You know that as R tends to infinite, Q also tends to infinity, and root L over C is the characteristic impedance of the system, of the network. And at resonance, the magnitude of the impedance of the inductor is omega naught times L, which is L over root LC, which is root of L over C, and this also is the magnitude of the impedance of the capacitor. Okay, so what you'll see is basic forms of Q are, you'll see Q equals R over root of L over C, and you'll see Q equals R over, which is R over omega naught times L, and you'll see R over, which is omega naught RC. Okay, so these are the different forms of Q. Now, one thing to be beware of, some of you might have thought that the inductance and the capacitance completely cancel each other out. Note that I said that their impedances cancel each other out, but you should be very careful, because remember that there is energy flowing back and forth between the inductor and the capacitor. So you should be beware of branch currents. Let's try to calculate the currents through the inductor and the capacitor. Okay, what you'll see is, if you try to calculate it, you'll find that the current through these two are, what is this? It's V out over omega naught L, which is right. What is this? I in times Q. Okay, so what that means is, if your Q, let's say the Q of your network is 1000, if you have an input of 1 milliamp, your current through your inductance and capacitance could be 1 amp, which is huge. So what you notice is very large currents can flow, right? And it is dangerous to think of the L and C as cancelling each other out. And now what this means is, careful layout. Okay, that is, if you have a 1 amp, if you have a very thin wire, for example, we'll be looking at layout where the width of these current lines would matter a lot. So if you design, so any wire having a certain width or thickness has a certain current density beyond which it will melt, it will heat up and melt. So if you're not careful, you could just burn out either the inductor or the capacitor. Usually it's the capacitor which is the first to go, because inductor already, as you'll see in one of the next few classes, it's already made with pretty wide traces, whereas the capacitor is often made with much thinner lines. So you need to make sure that you have current carrying capability. Okay, okay, now let's look at a few more relationships between Q. So let's look at bandwidth and Q relationship. So to do this, what we'll do is, we'll calculate the impedance close to resonance. Okay, so what we'll do is, let's take a frequency which is omega equals omega naught plus delta omega, and what we're going to do is, we're going to calculate, we know that y of omega is 1 over r plus, okay, we're going to calculate y of omega naught plus delta omega. So first, what is this? It's 1 by r plus j over omega L into omega square LC minus 1. Okay, omega naught plus delta omega whole squared LC minus 1, and you can expand this further, 1 over r plus so what you're going to do is, one plus delta omega over omega naught times omega square LC plus 2 omega naught delta omega LC plus delta omega squared LC minus 1. Now what do we know about this? We know that omega squared at omega, we know that omega naught is 1 over root LC. So these two terms cancel each other out. Okay. Then we'll take out some common factors. Omega naught, delta omega, and LC. Okay, what is left? Omega delta omega. So you have 2 here plus delta omega over omega naught. So what do we know? We can cancel some more terms. So omega naught L. So omega naught L. Okay, so we cancel those also. And then what we're going to do, what is 1 over 1 plus x? When x is very small, it's 1 minus x. So we're going to take this term to the numerator. Is r plus j. So what do we have left over? So we have delta omega times c. Okay, so and this is 1 over r plus j delta omega c, 2 minus 2 delta omega over omega naught plus delta omega over omega naught. And now we notice that there's a delta omega term outside, and since delta omega is small, we're going to neglect all of these higher order terms. Okay, so what this means is this is approximately 1 over r plus j 2 delta omega c. Okay, what does this mean? The equivalent circuit around resonance, it's similar to an RC, but RC parallel network, but impedance R and the capacitance is 2C. Okay, so what does this mean? And what you'll see is you can do the same thing for y of omega naught minus delta omega, and you'll get a similar equivalent circuit. So if you try to plot the admittance around resonance, so you have omega, and so the impedance goes something like this, and let's say you have so we know this is 1 over 2 RC, and let's say we're looking at the 3 dB bandwidth. Let me make this a little bit. Okay, and by symmetry we know this is also 1 over 2 RC. So total bandwidth is 1 over RC, and let's look at what is omega naught over bandwidth. We know omega naught is 1 over root LC, bandwidth is 1 over RC. Okay, so this is R over root of L over C, which is, we know this expression now, it's the Q. Okay, so Q for a parallel RLC network is also omega naught over bandwidth. So we have different definitions for Q. So we looked at the fundamental physical definition, which is omega naught times E total over average power dissipated, and as you'll see, this is the physical definition. Okay, and it's also applicable to distributed systems and let's say also non-resonant systems such as LR or RC networks. Okay, you can talk, if you don't have, even if you don't have any capacitances, you can talk about Q of those networks. Then we looked at Q is imaginary part of Z of omega over real part of Z of omega. Okay, this is another definition of Q. You actually get this from, if you go back, and we actually got it as in terms of the admittance, but you can get it in terms of the impedance also. So this is another fundamental definition. And then you have Q equals omega naught over bandwidth. And then you have a fourth definition, which is omega naught by 2 times d phi over d omega, where phi of omega is the phase of the open loop transfer function. Okay, so we sometimes use this to define the Q of some circuits like oscillators. But if you look at simple RLC circuits, these expressions are actually identical. You can derive each one from the physical definition. Okay. However, if you take more complex resonant systems, let's say they have more than one inductor or capacitor, or they are not simple RLC networks, RLC parallel or series networks, what you'll find is the Q which you calculate or determine from the physical definition is different from the Q you get from, for example, omega naught over bandwidth. And in many cases, you may what you can determine or what you can calculate is one of either 1 or 2. However, what you might be interested in is because you're interested in narrowband amplifiers, for example, you may be more interested in the third definition. Okay, so now a quick look at series RLC networks. So let's say you have an impedance voltage Vin being applied to a series RLC network. So let's say the voltage across the inductance is VL and voltage across the capacitance is VC. So you know at low frequencies the network is going to be capacitive, and because the capacitance impedance is going to dominate, at very high frequencies the system is going to be inductive. Okay, and at resonance the impedances of your inductance and capacitance are equal and opposite, and they cancel each other out. So what does that mean? It means that VL plus VC equals 0. Okay, and all the input voltage appears across the resistor. You can show that Z of omega is, let's say at any frequency, Z of omega is R plus j omega L plus 1 over j omega C. Okay, and you can proceed in the same manner as we did for the parallel network and show that omega naught is again 1 over root LC, and remember f naught is 1 over 2 pi root LC, and the network at omega naught network behaves purely resistive. Okay, now if you try to plot your Z of omega magnitude, so we know that it's very high impedance because it's capacitive, and it goes like this. Okay, and at resonance it's equal to R at omega naught. Similarly, if you try to plot the phase, so it starts off at minus 90, and this is the angle of Z of omega. And I want you to prove for yourself the analogous case, very easy, which is the voltage across the inductor and the voltage across the capacitor are both the input voltage times Q. Similarly, there we saw it was the current through the inductor and the capacitor was Q times the input current. Here it's Q times the input voltage. And what that means is, it's not just a short, right? You actually have very large voltages that can be developed across the L and C. And what we'll see is useful for what is this? So if you have Q times, if you apply VL, V in, and you get Q times V in across the inductor or the capacitor, we'll find that it's very useful for LNAs. Why? Because it's a passive voltage amplification, right? Okay, so it's not just a short. When we get to the LNAs portion, we'll look at this in more detail. Okay, so that's it for today.